Welcome to the final section of this survey course called Acids and Bases. Now, I mentioned in equilibrium that this was setting up the structure for acids and bases. And you'll see it applied as we do the constants for the application of the acids and bases. Start off with is the definition of an acid and base. Now, there are two principal groups involved. One person, Arrhenius, which was the first one to come out with a definition of an acid. He said an acid is some solution that produces hydrogen ions and a base produces hydroxide ions. Bronsted-Lowry, later group, went a little bit further by saying that an acid is a proton donor and a base is a proton acceptor. And of course, when you start talking about that, you're talking about water, since all of this is primarily water dissolved. Acids and bases are very, very much water solutions. Now, the acid dissociation constant, again, we're into constants. I told you when we started equilibrium that it's going to be constants galore. Anyway, the dissociation constant is set up right there in front of you. It is reasonably straightforward. The Ka is equal to the hydronium ion concentration. The H3O plus is called the hydronium ion. When water dissociates, it breaks down. And when acids dissociate, they break down in water solution. Anyway, the hydronium ion times the negative acid ion over the acid itself, HA. And you can write it without the H3O and just put hydrogen ion. Now, the basic expression for equilibrium for acids and bases is right in front of you here. HA aqueous plus H2O. Remember, water is paramount of importance in virtually all of this. In equilibrium, has the hydronium ion plus the conjugate base, whatever the negative ion is. Now, when these dissociate, the acid dissociates in water, water being the basic solution, because water is amphoteric. I guess that's the next thing I'll add. Amphoterism refers to a substance which under varying conditions can act as both acid and in other conditions can act as a base. Water's the principal one because it's the most involved. But under certain conditions, it acts as an acid or a base. Anyway, the dissociation goes to the conjugate acid, which is the H3O, and the A minus, which is the conjugate base. And it's in equilibrium, so it can go back and forth. Now, the constant for water, or the Kw, is the concentration of the hydrogen ion times the concentration of the hydroxide ion. And that'll equal to 1 times 10 to the minus 14th, which is your constant. Now, I mentioned amphoterism. Let's take the hydrogen ion concentration times the hydroxide ion concentration equals to 1 times 10 to the minus 14th. If you don't know either one of them, excuse me, and give them both the basis of x, then you've got x squared equals 1 times 10 to the minus 14th. And for those of you that got through second year algebra, and if you didn't, go back and review it, if you go log base 10 for an analysis of that expression, you come out with a functional answer of 14, or for 1, but there's two of them, two x's, and they're times each other, so it's x squared. So x would equal 1 times 10 to the minus 7th. And thus, we say that if we change that with a log function base 10, that x is equal to 7. So the pH of 1 times 10 to the negative 7th is 7. Now remember that, because pH, very important in acids and bases. All right, and I go through how you do that. Log base 10. Strong acids dissociate almost instantaneously when put in water associated. The waters being the greatest dissociated impetus for a strong acid. Okay, and the example I give is hydrochloric acid, that's stomach acid from your stomach, plus water forms a hydronium ion and a chlorine ion. Now, that's really quite important to you, because the hydrochloric acid, as I mentioned quite early in the course, is so strong when it's generated by the glands in your digestive tract that you could take it straight from the gland, put it on the back of your hand, and blister your hand. It's that strong. And if it wasn't for the mucus layer of the digestive tract, there would be a lot of burned holes in the lining of the digestive tract. But the mucus layer is pretty much impervious to acid, and that allows your digestive tract to work and you digest food, which is always nice. Okay, strong acids, most organic acids, also dissociate rapidly in water. Now, the weak acids, not so much. You've got HNO2, which is a weak acid, plus water, goes to form the hydronium ion plus NO2. Now, we say this is weak acid plus water forms the conjugate acid, H3O plus, and the conjugate base, which is NO2 minus. Now, another way to express this, Hb plus H2O goes for H3O plus B minus, which is the base. Ionization constants are important in all of this, so realize that from the beginning. Now we'll go back and we'll cover a weak base. The ammonium ion NH4 plus water in equilibrium forms the hydronium ion plus NH3, which is a strong base. Now, except for column 1 and 2 elements, most cations, you can almost think of it as metallic ions. They form weak bases. And quite a few of them are later thought of as spectators in chemical acid-base reactions. Now, I use an illustration for that where you got zinc complex, H2O4, which is a 2 plus ion, which is a very, very weak base, plus very, very weak acid, my bad, plus water being amphoteric, it can step up to the plate and form the hydronium ion and the zinc 3 water complex with a hydroxide added. Removes the water and puts a hydrogen on the H3O. The other hydrogen goes to the oxygen to form the OH ion. Now, the equilibrium constant, or the Ka for this weak acid, is Ka is equal to the concentration of the hydrogen ion over the concentration of the B, whatever that substance is, divided by the concentration of the acid. For a weak base, and of course we always use the ammonium ion because it forms a strong base as a product. The Ka is concentration of 1 times the concentration of the second over the ammonium ion, and the pKa, which we're trying to find in this, is equal to the negative log base 10. Go back and really what you can do is, if you got your old chemistry book, in the back they'll have the log base 10 conversion, and some of them have natural log stuff too. So the back of the book of most of the older chemistry textbooks before the vast innovation of the electronics, you had to have these things available. Now, when I first got into this business, kids carried around a logbook that had all that stuff in a book, separate book, as a resource. And you took it to all your physics, and your chemistry, and your math classes. It was your reference. Now, excuse me, they couldn't punch it up on a phone like you can. But this is a very basic course. I suggest you use the basics first, and then later on for speed, you can go to your electronics. Anyway, back to what I was speaking of. The equilibrium constant for the weak base comes out to be NH4 plus. The Ka is 5.6 times 10 to the minus 10th, and pKa is negative log 10 base 10. I think that should be -6, if I'm not mistaken. I think I may have written that one down incorrectly. Let me double check here. Yeah, this is incorrect. I might as well correct it now so I don't have to deal with it later. All right, moving along, we got a weak acid, HNO2, dissociates to hydrogen ions and the NO2 minus ions in equilibrium. The Ka is equal as we did it before. The NO2 has a lookup value. In other words, you can look up the value for the acid as 6 times 10 to the minus 4th. The pKa is again equal to negative log base 10 of 6 times 10 to the negative 4th, and it comes out to 3.22. Now, kind of ingrain these things in your thought patterns. Both weak bases and acids form conjugates. Bases accept protons from the water to form the hydroxide ions. Now, the acid-base chart for pH is right here. 0 to 14. 0 acid, 0 to 7 is very strong to weaker to neutral at 7. 7 to 14, weak to non-existent. Base is just the opposite. From 0 to 7, they're extremely weak or non-existent. And from 7 to 14, they're quite strong. So this gives you an insight to the introduction to acids and bases. Most everything we deal with in general chemistry is salts and weak acids and weak bases. Now, there is a reason for that. Because you get almost 100% dissociation when you put a strong base or a strong acid in water, then it removes any partials. Thus, the need to evaluate the resulting solution is non-existent because it's 100% dissociated. So partial dissociation drives the rest of the problems that you would deal with in acids and bases. Okay, this is the first of the last section in this course, and I hope you picked up a few things. I am providing this to you as a method for kind of dry running a chemistry course, survey course. I know I'll have my detractors about my lack of depth with this course, but again, from the beginning, I said it was a survey course, which means I was going to touch the high points of the concepts that were necessary for a survey course. I purposely have not gone into the weeds very deep in any facet of this course. The only thing I've really spent more time on than a normal chemistry course would is water. As I've said from the beginning, water is an extraordinarily important substance to your existence, to the planet's existence, and definitely to chemistry. So the next one will be the last one. So I hope you enjoyed it so far. You got one more to put up with me. Now, I purposely have not had quizzes or tests throughout all of this, since this is not an attempt to evaluate your understanding. It's to trigger your reading more, finding as much from textbooks that this information allows you to evaluate. And thus, when you take a course in general chemistry, you're one up on everybody because you've already gotten the tidbits of each of the different concepts. And hopefully it's helped you.